Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss about the vector equations of planes. We are going to construct the vector equation of planes analogously what we have done for the lines. The idea of the vector equation of the line or the plane is to figure out the vector which points out to the points on the lines or in the planes. For the line, we need a vector, one vector which points out to this line, and one vector which is parallel to this. And by just combining these two vectors, we can figure out any point along this line. So for example, by just scaling this vector v and adding this to the r0 is always going to give us the points along the line. And this is what we want for the plane. So we would like to get some vector r which would give us the points along the planes. So let's assume now we are given some plane, and again, so there is a vector which points out to this plane. So previously, in order to construct a line, we need a vector which is parallel to the plane. Now we are going to need a vector which is perpendicular or orthogonal to this plane. So we're going to call this vector as a normal vector. So the n is going to be called as a normal vector, which is orthogonal to the plane. So which implies that this normal vector n is orthogonal to any vector along the plane. So what I want is I would like to find the general vector r which would give me the points on this plane. So I would like to find this green vector r, and I would like to express this using the n and r0. So we know, we've learned about how to find the subtraction of the two vectors, right? So if you just connect, if you just put the two vectors which starts from the same point and connect their ending points, essentially it is going to be simply the subtraction of these two vectors. So this is what we've got. So what we are going to get. So I'm just going to connect these two vectors, and if I connect this, so you need to remember that the resulting vector is always going to go from negative to the positive, right? So I would like to obtain the vector r minus r0. So it should go from negative r0 to the positive r. So this is going to be something like this. And this vector now, r minus r0, is on the plane. And I know that this vector, which is on the plane, is perpendicular to the n. So the normal vector is orthogonal to any vector along this plane. So we know the equation which enables us to relate these two vectors, which is essentially the dot product. So I know that if two vectors are orthogonal, then their dot product is equal to the 0 and vice versa. So I'm just going to multiply the n to the r minus r0 is equal to the 0, and that's going to be the equation of the plane, which is super easy. So let's do an example in order to understand this a little bit in better way. So the n times the r minus r0 is equal to the 0 is a vector equation of the plane that appears. So let's say we are given the point along the plane with the coordinates 2, 4, and -1, and also we're given the normal vector n with the coordinates 2, 3, and 4. I would like to find a vector equation of the plane. So I'm just going to substitute them into this equation and figure out the r. So again, the r is going to be some general vector with the coordinates x, y, and z. So it is going to give me the coordinates of the point along this plane. So the r0 is already given, which is 2, 4, and -1. So if there is a point on the plane, we can express this using the vector whose ending point is this point. And the n is going to be given as 2, 3, and 4, and I'm just going to substitute everything into this equation. So it is simply going to be x, y, z minus 2, 4, -1. And all of this thing is multiplied as a dot product to the 2, 3, and 4, and this should be equal to the 0. Okay, so I don't have a space there, but this is equal to the 0. So this dot product is going to be multiplied to the first vector and to the second vector separately. I'm just going to multiply these two vectors separately. If I multiply 2, 3, and 4 to the first vector x, y, and z, I'm just going to multiply them component-wise and add them. That is going to be equal to the 2x plus 3y plus 4z minus, now I'm just going to multiply the second vector, the red vector, into the normal vector 2, 3, and 4. Again, I'm just going to do this component-wise. 2 times is a 2 plus 4 times is a 3 minus 1 times is a 4, and that's equal to the 0. Then I'm just going to simplify everything out. It's going to be 2x plus 3y plus 4z. It's going to be 4 here. This number is 4. This number is 12. And this number is minus 4. So it's going to be minus 12 here. Minus 12 is equal to the 0. Well, that's the vector equation, or that's an equation of the plane which is more convenient for us, right? So we obtain this from the simple equation n times the z r minus r0 is equal to the 0. So in the linear equation, I would say the of the plane is going to be denoted as the ax plus by plus cz plus d is equal to the 0, where a, b, and c are the coordinates of this normal vector. A, b, and c. So this is what we are going to define the normal vector always. So we are going to define the coordinates of the normal vector always as a, b, and c. And whenever you're given the equation of the plane, you need to understand that the coefficient before x, y, and z are going to give you the coordinates of the normal vector. Always. So we are going to use this information in order to solve the following problem. So let's say now we are given two planes, x plus y plus z is equal to 0, and x minus 2y plus 3z is equal to 1, and we would like to figure out an angle between these two planes. So we can't really find the angles of the planes between the two planes. We don't have such a formula, but we've got a formula which enables us to find the angle between the two vectors, right? So the normal vector of the first plane are going to be the coefficient before x, y, and z, which is the n1 is going to be equal to the 1, 1, and 1, which is going to be the perpendicular to the first plane. And the normal vector of the second plane, it's going to be equal to the coefficients before the x, y, and z for the second plane, which is going to be equal to 1, minus 2, and 3. Well, the angle between the two planes is the same as an angle between these two normal vectors. And just using this information, I'd like to find the angle between them. So I'm just going to use the formula of the cosine of the angle between the two vectors is equal to the n1 times to the n2 as a dot product, divided to the length of the n1 times to the length of the n2. So let's find all of the attributes for this formula. So essentially n1 times to the n2, which is the dot product between the two vectors, where I'm going to multiply these two vectors component-wise and then add them. It's going to be 1 times is a 1, plus 1 times is minus 2, which is minus 2, plus 1 times is a 3, which is going to be 3. So 1 minus 2, it's minus 1, plus 3, it's going to be 2. So the length of the n1 is going to be equal to the square root of 1 in the square, plus 1 in the square, plus 1 in the square, which is simply the square root of 3. And the length of the second vector, it's going to be the square of the 1, plus the square of the minus 2, which is 4, plus the square of the 3, which is equal to the 9, which is going to be equal to the square root of 15. Right? So I can express this as the square root of 3 times the 5 as well. So now if I find the cosine of the angle between the two planes, it's going to be equal to the 2 divided to the square root of 3 times the square root of 3 times the 5. Well, I can take out this 3 from the square root. It's going to be 2 divided to the 3 square root of 5. Then you can use a calculator to find the arc cosine of this number in order to find the angle between the two planes. Well, that's how we are going to find the angle between the two planes. And that's an equation of the plane which can be obtained using the two vectors. Essentially, one vector which points out to any point on this plane, and another vector which is orthogonal to this plane. Well, this is what I wanted to discuss with you about the vector equations of the plane. Thank you very much for your attention, and I hope that this was helpful for you.